Hello students, welcome to the class of Control System 2 followed by the code EE603. Introducing myself, I am Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today we will discuss on the linear transformation on state variables. During this video, we will discuss the introduction, the linear state transformation and linear systems, the modal transformation, diagonalization with the examples and the references. So far we have been seeing that the parallel form of realizing a system results a diagonal system matrix A. Now this transformation or the linear transformation describes the general procedure to transform the state variable model into an alternate model using the state variables. And state transformation, or it is a change of the variables. It is used to simplify a calculation or to gain insight to a phenomenon. Now, if we consider the situation of changing from one existing state representation to a new state representation Z by the n by 1 vectors. Now, the transformation must be invertible and it can be represented by x is equal to tz, which implies z is equal to t minus 1 x. And in the case of the linear transformation, T should be the n by n invertible matrix. And if we use the nonlinear transformation, we will use the notation phi is equal to t minus 1. So here in this video, we will consider the similarity transformation and the diagonalization of the system. So first we consider the state transformation from x equal to tz to convert the linear system. Now, if we consider the state model, then the system can be defined by a state model through the equation x dot is equal to ax plus bu and y is equal to cx plus du, and most of the cases d may be the 0. Now, in this form, the diagonal matrix A has the advantage that each state equation is a function of only one state variable. So hence each state equation can be solved independently and therefore the equations are said to be decoupled. And this decoupling feature of the system is very useful in the analysis of this system. So here we have considered the x dot is equal to ax plus bu and y is equal to cx. Now we are interested in transforming this dynamic equation into another set of equation of the same dimensions. So let us define a new state vector, that is z, which is related to the state vector x, and it is a n by n non-singular matrix T, so that the tz dot is equal to atz plus bu and y is equal to ctz. So we can write from this equation T can be divided by the right hand side and z dot is equal to T inverse at z plus T inverse b into u and y is equal to ct into z. So or we can write this equation z dot is equal to a hat z plus b hat u and y is equal to c hat z. So we desire the transformation so that this T inverse AT is the diagonal matrix. With this condition, the matrix T is the diagonalizing matrix. Now if we consider the matrix A and the matrix A hat, then they are similar because they have the same spectrum, and for each choice of the T we will obtain the different but the equivalent mathematical description of any given system. So here you can rewrite this equation in another domain, that is z dot is equal to a hat z plus b hat u, and y is equal to c hat z plus d hat u if d is present. So from this we can write that this T inverse AT is equal to A hat, where T inverse B is equal to B hat and CT is equal to C hat, but D hat remains unchanged. Now if we find out the eigenvalues of the diagonal matrix or A hat matrix, then the eigenvalues will be same as the eigenvalues of the A matrix. So if the eigenvalues of A matrix is lambda 1, lambda 2 and lambda 3, then the eigenvalues of A hat will also have the same eigenvalue, that is lambda 1, lambda 2, lambda 3. And this transformation which we have discussed in the slide is known as the similarity transformation. And since in the transformed system, such properties as the characteristic equations, the eigenvalues, the eigenvectors and the transfer function remain invariant, so it is known as the similarity transformation. Next is the modal transformation. So here we have written that A equal to E into A inverse, or E inverse A E equal to A. So it will be the diagonal matrix whose diagonal entries are the eigenvalues of A in some order, and E is the matrix whose columns are corresponding eigenvectors in the same order. So as we have discussed earlier, this x dot is equal to ax plus bu and y is equal to cx, or we can write the z dot is equal to a hat z plus b hat u and y equal to c hat z. So now this matrix T or this E can be written as from the eigenvectors of the system matrix A, and where this B hat is equal to E inverse B, or it may be written as T inverse B or P inverse B, and C hat is equal to C into E, and C hat I is the ith column of the C hat, and in this representation each component of this transformed state vector Z is decoupled from the other components, and so it makes the computations more transparent. So each state equation can be solved independently, and therefore these equations are said to be the decoupled, and this decoupling feature is very useful in the analysis of the system, and hence it is desirable to make matrix A diagonal so as to have the decoupled equations, and if this A is not diagonal, we can transform the state variable such that the resulting matrix A is diagonal. So in this way of transforming a non-diagonal matrix to a diagonal matrix is known as the diagonalization. Now when it should be a diagonalizable? So if a square matrix is A, and it will be diagonalizable if there exists an invertible matrix P, so that P inverse AP is a diagonal matrix. So now we will consider two different matrices. One is A matrix, another is A hat matrix, which is the diagonalized matrix. So among these two matrices, it will be similar, but it is not confirmed that if only the eigenvalues are same, then these two are similar. So only it is not considered that the eigenvalues are same for the diagonalized matrix. So if a n by n matrix A is diagonalizable, if and only if A has linearly independent eigenvectors. So if the matrix A and B both are n by n matrices and A is similar to B if there is an invertible matrix P, so that P inverse AP is equal to B, and this changing from A into B is also known as the similarity transformation. So next is the process of diagonalization. How to diagonalize a non-diagonalized matrix into a diagonal matrix. So first we need to find out the characteristic polynomial of the system, and after we get the characteristic polynomial or the characteristic equation, we will find out the eigenvalues of the system. Once we have find out the eigenvalues of the system, we will find out the eigenvector of the system. So suppose a system matrix is given of 2 by 2 order, then there will be 2 eigenvalues, and for each eigenvalue we will find out 2 eigenvectors. Then we will combine all the eigenvalues and then all the eigenvector with respect to that eigenvalues, and then we will create the modal matrix P. And if this P matrix or the modal matrix is orthogonal, then this P inverse AP will be the diagonal matrix. So let's take one example of diagonalization. So here A matrix is given, and from this matrix we can say it is not in the diagonalized form, because diagonalized form means the corner elements will be the eigenvalues and the upper half element will be 0. So we have to diagonalize this matrix A. So this matrix has the maybe the features that it should be a diagonal matrix, and the main diagonal elements which will be the distinct roots or the eigenvalues of the matrix. So first find out the poles or the eigenvalues of the system. So to find out the eigenvalues of the system, we need to find out the characteristic equation, and the characteristic equation of any system can be found out by using the equation determinant of Si minus A or A minus lambda I is equal to 0. Here we have used that determinant of A minus lambda I is equal to 0. So the A matrix is given as 1, minus 1, 2 and 4, and this lambda, it is the eigenvalue, it will be the result will be the eigenvalues, and now it is a scalar, and identity matrix of 2 by 2 has been chosen, so it is 1 0 0 1. So if we perform this A minus lambda I, then it gives us 1 minus lambda minus 1, 2 and 4 minus lambda equal to 0. Now we have to find out the determinant of this. So it gives the result lambda square minus 5 lambda plus 6 equal to 0. So this one is the characteristic equation of the given system. So the solution of the characteristic equation gives us the 2 poles of the system or the 2 eigenvalues of the system. So the 2 eigenvalues of the system has been found that lambda equal to 3 and lambda is equal to 2. So if we choose the lambda equal to 2, so that is the first eigenvalue. So for the first eigenvalue, we will find out the first eigenvector for the given system. So to find out the eigenvector, we will compare Ax is equal to lambda x, where x is the eigenvector and lambda is the eigenvalue. So we will rewrite the equation in this form. This is the A matrix into Ax is equal to lambda into x, or we can write the equation 2x plus 4y is equal to 2y, or x is equal to minus y. So now if we consider y is equal to 1, so x will be minus 1. So the first eigenvector will be minus 1 and 1. Similarly, we will find out the eigenvector for the second eigenvalue, that is equal to 3. And if we find out, then it will gives us the result P12 is equal to 1 minus 2. So these two are actually two eigenvectors for the given system. So next we will find out the modal matrix, and this modal matrix is nothing but the matrix whose columns are the eigenvectors of the system. So the first column is the first eigenvector P1 and second column is the second eigenvector P11. So in this way we can find out the overall modal matrix P, that is minus 1, 1, 1, minus 2. Next we will have to find out P inverse AP. So P inverse becomes 1 by mod P into adjoint of P, or P inverse AP becomes 2, 0, 0, 3. So this matrix can be written as the D matrix or the diagonalized matrix, and its corner elements or the main diagonal elements are the eigenvalues, which is 2 and 3, and the remaining elements are 0. So this technique of transforming a non-diagonal matrix to a diagonal matrix is known as the diagonalization of the system. So these are my references. I hope after this video lecture you have a clear idea about today's topic. Now we will go through some question answer session in the context of this video lecture. So you are requested to go through it gradually and solve it by your own. The answers of the questions are attached at the end of each question.